Example 4 is a fairly typical sort of question you might see on the AP exam. It gives you a lot of information. In fact, I think it gives you exactly the information you need to answer the questions. Nothing more, nothing less. So it gives you the value of a function at 2, the value of its derivative at 2, second and third derivatives all at x equals 2. So that's exactly what we would need if we wanted to write the degree 3 Taylor polynomial, only if it was about the point x equals 2. If this were something other than 2, then we'd be out of luck. But what are the odds? They gave us the exact x values here, 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 and here that we needed to deal with that. So we know that the Taylor polynomial of degree 3 of x is going to be equal to f of 2, which is 6, plus f prime of 2, which is 4, times x minus 2 raised to the first power divided by 1 factorial. And then the next value, the next coefficient is negative 7. I'm going to write it up here because I'm anticipating a denominator of 2 factorial. And x minus 2 is going to be squared. And then the next coefficient is positive 8, so I'll put an 8 here in the numerator, and then we put a 3 factorial, or a 6, on the bottom, and we've got x minus 2 to the third power. All right, now if you feel like it, if it makes you happy, you can reduce that 8 over 6, but there's no particular reason for you to do that unless it asks you to reduce the fractions, but there's no need to reduce it. In fact, if you had written this as 7 over 2 factorial and 8 over 3 factorial, that would have been pretty good too. So whatever you write, as long as it's correct and reasonably reduced, then there's no problem there. So keep that in mind. Don't waste time reducing. Of course, I wasted more time explaining that you don't have to reduce than it would have taken you to reduce 8 over 6, but hopefully you get the picture. All right, so now we're going to use this Taylor polynomial to approximate f of 2.3. So f of 2.3 does not equal p sub 3 of 2.3, but they are approximately equal to each other. That's the whole point of Taylor polynomials, right? So we have p sub 3 of 2.3, and I'm just typing this into my calculator because I don't feel like writing it all out. So x minus 2 cubed, and then we will wait for my slow calculator and find that when x equals 2.3, we should get an output. I should probably do an approximate here, approximately equal to 6.92. Maybe I can get a little bit more accuracy here. Hold on just one moment while I battle with this calculator. Oh dear. It's not working for me. Nuts! All right, 2 decimal places it is. Oh no, but it says 3. Hold on, I can do this. I will persevere. I am here for you guys. I will do it this way, and then I find that last decimal point before we round is 1. All right, fantastic. All right, so that is what f of 2.3 is approximately. So that is part A finished. Okay, we haven't used the error bound yet, but we are about to. It says the fourth derivative satisfies that inequality. The fourth derivative of the function evaluated at x is always less than or equal to 9 for all x in the closed interval 2 to 2.3. What a perfect piece of information we are given. Why is this perfect? For several reasons. One, the fourth degree is 1 bigger than the 3, n plus 1. Okay, so this is n plus 1. And what's the other perfect thing we're given? We're given an inequality here that tells us an upper bound for that derivative. So that's another nice thing that we're given. And then lastly, this closed interval is exactly the interval we want to that we need because c equals 2 and x equals 2.3. So we don't know what happens outside of that interval, but we don't care what happens outside of that interval. So what are we going to find? We're going to find the Lagrange error bound, r sub whatever n was, still is, 3, evaluated at the x value of 2.3. Okay, and according to the Lagrange error theorem, we have the next derivative, so the fourth derivative, evaluated at some value z. Z is some number between 2 and 2.3, divided by 4 factorial, and then multiply that by x minus c, or 2.3 minus 2, raised to whatever n plus 1 is. In this case, it's 4. Okay, and we don't know what that fourth derivative is at z because we don't know what z is, but we do know that guaranteed this is the maximum it can be. It can't be any bigger than 9. So we're going to say this is definitely less than or possibly equal to 9 over 4 factorial times 0.3 raised to the fourth. And when I type that into the calculator, I get, let's see, 9 divided by 24 times 0.3 raised to the 4. I get approximately 0.003. You should be pretty used to the fact that these numbers are small. All right, so that would be, again, all they need for part B, right? No, I take it back. That's not all they need, because then they say find the interval A to B such that f of 2.3 is definitely in between there. So we can say that A is equal to our approximation, and since A is the lower bound, we're going to subtract our maximum error. So that's equal to, let's see, we had 6.921 minus 0.003, so that's 6.918. That's my A value. My B value, we're going to do the same thing, except we're going to add our error. Okay, so that's 6.921 plus 0.003, so that's 6.924. So we know that that the lower bound of 6.918 is definitely less than or possibly equal to f of 2.3, which is definitely less than or possibly equal to the upper bound of 6.924. So don't fall for it like I almost did. Make sure you follow through and answer the question that they're asking. All right. And then lastly, this is the easy question. If you've done all the hard stuff right, then all you have to do is answer the question, is 6.992 within your interval? 6.9, well, that's close to those values. Those are the lower and upper bounds here are both 6.9 something. But the largest these values ever get are 6.92, whereas this is 6.992. This is too big. So f of 2.3 is definitely positively not equal to 6.992, because 6.992 is not in the interval that we discussed on part C. So that would be a decent explanation for why f of 2.3 is definitely not 6.992.